Hello and welcome. Today we're going to dive into a question that people have been asking for literally thousands of years. What is everything actually made of? We're going to go on a journey from ancient philosophy all the way to the first chemical labs to uncover the amazing story of the atom. So let's jump right in.
So, here's our game plan. We're going to follow the trail of clues, kind of like a detective story. We'll start with a really old idea about something indivisible. Then, we'll look at the first scientific laws that provided the hard evidence. After that, we'll see how a guy named John Dalton put it all together, which led to a whole new theory of matter.
All right, so our story doesn't start in some fancy lab with bubbling beakers and all that. No, it starts way, way back, over 2,500 years ago, and it starts in the minds of philosophers. I mean, really think about it. If you take a piece of paper and cut it in half, and then cut that half in half, and just keep going, do you ever get to a point where you just can't cut it anymore? That simple thought experiment is what sparked one of the biggest ideas in all of human history. And what's so cool is that brilliant people in totally different parts of the world were thinking the same thing. In ancient India, they came up with the Parmanu. Over in ancient Greece, they called it atomos. Different names, but the exact same idea. There must be a tiny, fundamental particle that you just can't break down any further.
But for the next 2,000 years, that's all it was, an idea. A really powerful one for sure, and a great thought experiment. But there was no way to prove it, no way to test it, so it was basically a really, really good guess that had to wait for science to catch up.
Okay, let's fast forward to the late 1700s. This is when science starts to change. It's less about just thinking about things and more about carefully measuring them. And this is where our little detective story gets its first real, solid clues, thanks to scientists like Antoine Lavoisier.
So the big puzzle for these scientists was what actually happens to stuff when it changes? When wood burns or iron rusts, where does the matter go? To figure this out, they started doing some incredibly careful experiments.
Check this out. This experiment is so simple but so brilliant. They'd take some chemicals, seal them up in a flask so nothing could get in or out, and weigh the whole thing very, very carefully. Then, they'd mix the chemicals inside and let them react. And when they weighed it again, the mass was exactly the same, every single time.
So what does that mean? It means matter doesn't just disappear. You can't create it from nothing and you can't destroy it. It just changes form. This became a fundamental rule, the law of conservation of mass. Clue number 1 was officially on the board.
But wait, there's more. That wasn't the only weird thing they noticed. Chemists like Joseph L. Proust started realizing that when elements combine, they don't just mix together randomly. It's more like they follow a super strict recipe.
Let's just take water. It didn't matter if they got it from a river or from rain or made it in the lab. When they broke it down, they always found the exact same ratio. For every 1 gram of hydrogen, there were always 8 grams of oxygen. Always. That's a pretty specific recipe, right?
And this led to our second big clue, the law of constant proportions. Basically, it means that a pure compound, like water, will always have the same elements mixed together in the same proportions by mass. It's a fixed, unchangeable rule. Okay, let's take a breath and see what we've got. We have this ancient Greek idea about tiny, indivisible particles. And now we have 2 new, proven scientific laws about mass always being conserved and compounds having fixed recipes. The stage is perfectly set for our hero, John Dalton, to step in and connect all the dots.
Now, Dalton wasn't some rich guy with a fancy private lab. He was a humble school teacher, came from a poor family. But in 1808, this teacher proposed a theory that was going to completely change the game for chemistry.
See, Dalton's stroke of genius was this. He looked at those 2 new laws, and he looked at that 2,000-year-old idea of atomos, and he realized they fit together perfectly. He saw that the idea of atoms wasn't just a fun thought experiment, it was the scientific explanation for everything they were seeing in their experiments. Take this point from his theory. If chemical reactions are really just about indestructible little atoms rearranging themselves, then of course the total mass never changes. Nothing is being created or destroyed. You're just shuffling the pieces. Boom. The law of conservation of mass is explained.
Okay, cool. So that explains mystery number 1. But what about that weirdly specific recipe for water, that fixed 1:8 ratio? How in the world does the idea of atoms explain the law of constant proportions?
Well, here's the answer, right in another one of his points. If a water molecule is always made of the same set combination of hydrogen and oxygen atoms, say 2 hydrogens for every 1 oxygen, then the ratio of their total masses has to be constant too. It's not magic,
It's just a consequence of the molecule's unchanging atomic recipe.
So, now let's put all these pieces together and look at the full picture. Let's break down the key points of Dalton's amazing theory, the one that tied it all together and gave us a whole new way of looking at matter itself.
Dalton basically laid out these 6 rules. He said, look, everything's made of atoms. You can't destroy them. All atoms of one element, like gold, are identical. Atoms of different elements, like gold and silver, are different. And they combine in simple, whole number ways to make everything around us. This single theory explained all the evidence they had. It just worked.
And this was a massive turning point for science. A huge revelation. The atom wasn't just some abstract philosophical idea anymore. Thanks to Dalton, it was now a real, scientific concept, backed up by hard evidence. The ancient mystery was finally solved.
So Dalton had cracked the case. He pictured atoms as these tiny, solid, indestructible balls, kind of like miniature billiard balls. But he also opened the door to an even deeper mystery. What if those little solid balls weren't so solid? What if there was actually stuff inside the atom? We'll get into that in part 2.